you all. In this lecture, we will discuss about the autoencoders. Before going to discuss about the autoencoders, let's remind this PCA, Principal Component Analysis, which we have discussed in statistical machine learning. So, what is the importance of principal component analysis? Is that it is used for simply dimensionality reduction. So you have a n number of features which are mostly sometimes it is not necessary. Whatever the data sets you have taken, it consisting more than 10, more than 15, more than 20. But among those, very few features are more important for classifying the data. And some features are which are not showing more interest upon the classification. So it is indirectly the wastage of dimensionality and unnecessary to go for the different mathematical calculations and getting the features. So therefore, in order to reduce the dimensionality of that feature space, that is while extracting the features, so this PCA is a better utility, that is we can useful for the dimensionality reduction. Here we are using statistical methods in the principal component analysis, and these statistical methods by using we are matching to reduce the while we are finding the covariance among the different principal components, and whichever is not necessary or having very less covariance, those are we can eliminate by manually or some other methods. So this especially used for the dimensionality reduction. And here this is the first one is a why we are going towards the encoder when there is a principal component analysis. Principal component analysis is simply supervised learning. Okay, the first the problem with the principal component analysis is it is a supervised learning, and which it requires a labeled data. And second one is the it is applicable on linear data. Okay, these are two points the PCA is having some limitations. Here, data must be a linear, and this having supervised learning only. Now come to the autoencoders, and one this is statistical method, right? Now autoencoders is the deep learning methods. It plays the role by using the neural network. It is again classifying the same. It will done the same dimensional induction, but here the advantage of the autoencoders is that it is unsupervised learning, means it doesn't require any labeled data, and it can applicable for the both linear and non-linear data also. That's the advantage of the autoencoders. The remaining is almost all means though both applications having same coming to the same meaning, but the only thing is that these are the differences: unsupervised learning and both linear and non-linear. Non-linear data. Okay. Now let us go with the some problem with the autoencoders. So here the definition, if I am taking the autoencoder, is a type of neural network used for unsupervised learning that we have discussed, primarily for dimensional reduction, feature extraction, and denoising data. So there where they will go for the denoising is when we are after encoding whatever the features we are extracted from there, we can find the unnecessary data. Otherwise, these features can be used for some different applications before going to the decoder. So because whatever the input, exactly the same as the output. Okay. So where we will use the features means in the bottleneck link. In the middle itself only, we have to collect these features and used for some other purposes. Okay. So here it learns to encode the input data into the compressed form and then reconstruct the original data from the representation bit. So I said it is compressing to the example. It has a 3 neurons, then that means 3 features. It may be converted into the 1 feature or 2 features. Again form into again 3 features at the output end. So input and output are almost all same. The only in the middle is that is called as a bottleneck. Okay, only 3 blocks in the autoencoder. Simple to remember. One is the encoder, another one is the bottleneck, and another final one is a decoder. So bottleneck, or we can call it as a latent space, it is a representation of a feature space. Okay, and it having a compressed information of the features. Okay, now take here very simple problem I have taken, that is uh, only 2 neurons at the input end, the same we have placed at the output end also 2 neurons, and whatever the information I am going to compress, that is 3 and 5, it has to be expected to obtain at the output also. In the middle, it is compressed to the single neuron, that is information features are compressed in the hidden layer. Almost we can call it hidden layer also, or latent space, or bottleneck. Okay. So this one, it is compressed and again decompressed to the back to the 3 and 5. So here I have taken x1 equal to 3, x2 equal to 5, and these are the weights and all biases I have taken. Okay. So all of you know that the basic neural net, how it will be calculated. The latent space, simply I have taken z equal to z x1 w1 plus x2 w2 plus bias. So this result we have obtained 2.7. Okay. After getting this one, then again I am writing this equation x1 bar, that is x1 bar is equal to 0.5 into, that is z plus b1, and 0.7 into z plus, that is x2 bar. X2 bar is a 0.7 multiplied with 2.7, that is z plus bias. Okay, these x1, x2, and we have obtained. But let us see here. X1 is 3, but we have obtained 1.55, and x2 is 5, we have obtained 2.1, and that means we haven't got the proper answers, and there is a loss. So when there is a loss, we are, obviously we have to go for the back propagation. So before going to go for the back propagation, we have to calculate loss function, that is here I have taken mean square error. So mean square error is obtained 4.993. There is a loss, is huge loss. Then we have to go for the back propagation. Okay. So this is the for the loss formula, x1 minus x1, because there are two measurements, x1 bar and x2 bar. So now in the back propagation, all of you know that we need to update these all weights, because there is might be a problem at any weight. So all weights has to be updated each iteration. So first I have taken W3 and W4 at output side, B1 and B2 also at output side, and this W1 and W at input side. Okay, how we can write this loss? Dou L by dou W3, it is simply dou L by dou X1 bar and multiply the dou X1 bar by dou W3. So here all we have all these things. X1 is the W3Z plus B, already we have discussed, and uh, then dou L by dou X1 means here we had a answer, that is with respect to x1, if I am integrating, differentiating, then we will get the answer. So the final answer we got minus 3.915. In the same way, dou L by dou B1, that is also dou L by dou x1, and in x1 we have a B1, sorry, this is a B1. Okay, dou x1 by dou B1, this we got. Likewise, dou L by dou W4, dou L by dou B2, all we are updated. This is one extension. These are all for the output side. And when I'm going for the input side, then first we have to go dou L by dou x1, dou x1 by this one we can write in dou z, sorry, okay, dou z1, dou w1. So if I'm do this all these calculations, finally I got minus 8.076. Okay, then likewise dou L by dou w2, dou, it's a small mistake. Okay, dou L, here it is a dou L, so please make it correct. It's not a dou z, it is a dou L. Dou L by dou W1, dou L by dou W1, and dou L by dou W1, dou L by dou W2, and dou L by dou B. So dou L by dou Z and dou Z by dou W2, dou L by dou Z by dou B. Because we have a Z having the function like this here, x1 W1 plus x2 W2 plus B. Okay. So here after updating all the this after taking the derivative of all these things, we have to go for the updates, that is W1 new, W2 new, B new, W3 new, W4 new. The formula for is a W1 new is a, that is stochastic gradient formula, W1 minus alpha into dou L by dou W1. So alpha here it is the learning rate. Okay, learning rate we have taken 0.01, very small learning rate to better convergence. Okay, this is the updated equations, updated weights and biases. Again, then in the second epoch, these all weights has to be changed, and again we will try and find about the loss. If loss is getting towards the 0, then we can ignore. If it is not possible, again we have to go for the all weights, biases we need to update. Again we will continue until loss become 0. So this may happen in the system. If I am writing a program for this one, it takes 20 to 30 iterations. but here only for the better simplicity, I'm explain only one epoch. Okay. Thank you.